so Otfried will give us his second lecture on multiple type quantum mechanics.
Okay.
Hello? Thanks. Okay, thanks for the invitation again. So, yes, today I will talk about the second part of my lecture about multi-particle entanglement. And yes, just to give you an overview, this was the structure of my lecture. This was the first lecture, mainly talk about pure states. Then today I mainly talk about mixed states, about different concepts, how to characterize entanglement in mixed states. And in the next lecture tomorrow I will talk mainly about graph states and similar related family like hypergraph states and so on. So, what's the plan for today? So, first I will talk a little bit about entanglement measures, which I did not finish on Tuesday. Yes, this is mainly again about the pure state case. Then I will just recall some basic facts about bipartite mixed states, which essentially Anna told us. It will be just more or less 2-3 slides about, yes, because this is what I need later for the rest of my talk. Then the main thing will be some criteria for multi-particle entanglement of mixed states. And then finally I will talk a little bit about network entanglement, how you can characterize entanglement in quantum networks. And I mean, as before, please interrupt me at any time if you have questions, so there's no pressure, I don't have to do all this stuff, so I'm happy to discuss questions.
You have to.
Why? Why?
I want to hear about network entanglement.
Okay. Sorry, good. Okay, good. Okay, this is not pressure from my side. So. You have to blame her. Good. So, let's start with some entanglement measures. And, okay, actually this is again showing some pictures. This is a cave close to Gühne. So, I will start with, I mean, there are many entanglement measures, and I will only mention 2. Yeah, because there are so many, I mean, if I will try to mention everyone. And the first thing that I want to mention is the so-called sweetening. What is this? So, remember from the first lecture, we asked whether we had something like a state and asked can it be transformed into something like a W state, for instance. Yeah? And we had said something, this was our SLSC classification, that we said, look, there's something like a JZ class, there's a W class, and there are some lower classes like the fully separable states. But one of the important questions was something like to check which states can be transformed to something like a W state. And this was the equation that we take here something like this is a W state, and this is something like some local operations, this SLOCC scenario, so they are more as arbitrary matrices, and applied to this state, they should be to the W state. And now we want to characterize more precisely the states that can be transformed. And if you look a little bit sharp, then this is just something like an algebraic equation. Because what is written here? We have something like this is a fixed state, I mean, these are just numbers. Yeah? This is the state psi that has coefficients. It's in the complex space, it has 8 complex coefficients with some normalization. And these are some arbitrary matrices. And I could also see this as something like one big matrix with some constraints, and it could be something like a triple. So all in all, you can say if you see this equation here, you have these are fixed parameters and these are variable parameters with a certain structure, and these are also variable parameters. So you can essentially reverse the question. You can ask, okay, what are the constraints for psi that there must be some solution of this type? This solution. Yeah, in principle, this in mathematics, this would be just some algebraic equation. You can try to solve that. And actually, in mathematics, so I will not go into details, there's this thing called Gühne basis. Has anyone of you heard about Gühne basis? Good. Yeah, so okay, as mathematicians, I suppose. Yeah, so of course they know. Yeah. So in principle, you can solve such equation. You can ask, okay, I have this system of equation. I want to ask the constraint of psi such that this ABC exists. This you can actually solve this with this theory of Gühne basis, and there are some computer programs doing this for you. Yeah. And then you can ask, okay, what's the constraint, and there will be some result which looks like that. Okay, this doesn't look nice, but okay, it's not so ugly. So in principle, what we ask, what does the concept imply that this is a solution? Well, psi has some coefficient aijk, and you find essentially you have to, from this aijk, you have to turn certain combinations, which are called D1, D2, D3, and you combine them, and the state can be transformed to the W state if and only if this is. So this is more or less the rewriting of this algebraic thing. And in principle, if you are lazy, if you're a mathematician, I don't know science, yeah? So you can really just, and you don't have to think about physics, yeah? I mean, that you really can say, look at plugins. There's in a plugin, there's really some computer algebra system that solves this, and after some minutes you reduce this equation, fine, we're done. Of course, this does not give you much physical insight, yeah? That's what I'm saying. Yeah? So, but this is just a solution of this thing, and this thing is called the 3D. Yeah, this is something like this. So what does it mean? You have no clear parameter telling you whether the state is in the W class or not. And given a state, you can just evaluate it. Again, it's a little bit ugly, but actually, if you look a little bit carefully, it's not so ugly, because you see from there, you have always somewhat like opposite things. You have 0, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, and so on, and these combinations. And here you have always 0, 0, 0, 1, 1, 1, and then two opposites as some opposite. So it's not entirely, I mean, it's not so ugly. Yeah? You can visualize actually on some cube and so on, so it's not completely. So in some sense, you can say you have solved this problem given a state, you can just observe it. So what was now the original motivation? Because this was not discovered in this way as I explained you now, this was discovered more by Kaufmann, Kuhn, and Gutas in this paper. And the original motivation was to look for things like monogamy rotations. So what can you ask? You can take, for instance, something like a three-partite state, and actually, here maybe that's not this. Yeah, so you have something like a three-partite state. And now you can ask, maybe I write it down. You have something like A, B, and C. And you have some state here. And now you can ask some more, what is this entanglement between A and the rest? And you should say this entanglement should be something like contained in as entanglement contained in this pair, plus entanglement contained in this pair, plus maybe some rest. And this is exactly the idea of these monogamy relations. So what Kaufmann, Kuhn, and Gutas proved that there's a relation between the entanglement of A versus BC, which is somewhat like this bipartition, but I put it there. This can be written as some entanglement of the reduced state. If I just look at AB, plus some entanglement of the reduced state, if I look at just AC, plus some remainder. This remainder is exactly the 3. And this was the physical motivation, how they proved it and how they found the formula, which is actually much more difficult, or it requires really some hard work and some addition and so on. Yeah, but this is somewhere you can see this as, that's why it's sometimes called the residual tangle, because it's something like the remaining tangle. Yeah, there's something of the maintained, if you have here this state, if you have something like this bipartite entanglement, but there must be some remaining really tripartite entanglement, and this is more or less. And you can, in this relation, then also, yes, see, you recover the JZ and the W class, yes, was the JZ class, or the JZ state. You have something like, as I mentioned, also on Q state, the bipartite entanglement is always 0 if you trace out one particle. Yeah, but this bipartite entanglement is actually large, so that means that this has a large detangle. So these terms are both 0. So this is 0, 0 plus 1. And on the other hand, for the W state, I told you that these two-body states, these marginals, are highly entangled, actually maximally entangled, maximally they can achieve. So you have essentially this thing is equal to this plus this, and this 3 tangle is 0, as I defined it on the previous. And so you can have two extreme cases which you cover in this page. And you use this sometimes also, I mean, my picture, I don't know, so of course this is much nicer plotted, but okay. So this, you can see that this is what he calls the residual tangle. Yes, something like a bipartite entanglement plus that, bipartite plus a bipartite entanglement. And here, this application would use something different, some different letters. Okay? Questions? Yes?
Can you just remind us what Paraty and then base C would be the Otfried. Maybe it's tricky, like how does it compare now?
So what do you mean compare with? Wait.
I'm just thinking like because Anna said when you have three parties, you can always bunch them together and look at it from a bipartite perspective.
Yes.
Like does it have some relation or?
I mean, okay, actually what it tells you is you can see there's something like that, there's some entanglement which cannot be covered by bipartitions. Because these three terms, they all essentially are something like bipartitions. Yeah, so either you take this bipartition A versus BC, or you take you throw away one particle and look at the bipartition because only have two particles left. So these three terms are all bipartite entanglement measures. But essentially this tells you, oh, there's something remaining. And you can exactly quantify it. It's not a vague thing that let's say, of course, there's always something remaining, yeah, but it's a clear formula that can say this is a term that is missing. Okay, good. So let's come to another measure of entanglement. And this is called the geometric measure of entanglement. What is this? This is a completely different approach, but I just want to also stress that there are different approaches and which are not easily met to just. So it's just very simple, it's a very simple definition. I just take some multipartite state and I ask what is the closest product state? Yeah, so I take the state and I take something like the maximal overlap of this product. And how do I calculate? I come to this later, but let's assume that. And that's it. And if my state itself is a fully separate product state, then of course this is 1, because then this is something like, we find the state itself as overlap 1. So what does it mean? So I can just say, okay, if this is 1, then the state is not entangled, and if this is maybe small, then it is highly entangled. So you take just 1 minus this quantity and call it an entanglement measure. Yeah, so you can also, because just to flip the sign. Sometimes you see also people taking the logarithm. Yeah, but okay, this doesn't really matter. And so, and this is what is called the geometric measure. And okay, you may ask, now, what do you do for mixed states? Yeah, I mean, okay, I don't want to talk too much about mixed states, but there's always this trick of this convex roof construction, which also Anna mentioned, namely, which is that somehow you take you're taking a state, you try to decompose it, and you're looking for something like the cheapest decomposition. And you learned also from Anna that this decomposition is by no means unique, so you have to optimize over all these decompositions, and yeah, this is something like can be ugly, and often you cannot do that, but in principle you can define it like that, and it has nice properties. Good. Okay. So, how can you somehow, what can you say about this method? Let's go back to the bipartite case. In the bipartite case, we know all that we still have the Schmidt decomposition. And the Schmidt decomposition looks like that. So the Schmidt coefficient is the states. And you can easily see that the closest product that you can get is just something like this product state that corresponds to the biggest Schmidt coefficient, which I always call S1, the first one. So this is, I mean, this is can relatively easily check because sometimes the maximum singular value of a certain matrix and there's some but so essentially for bipartite states, you just have to look at what the biggest Schmidt coefficient, and this is one of the geometric of this overlap. This is of course very easy to calculate because you can easily calculate the Schmidt coefficient. Now let's go through a multipartite case and let's look at GZ and W again. What do you know about the GZ state? Well, the GZ state looks like that. And now it's really important that I write down the normalization. Now what can we say? If we have something like the bipartition, I mean we want something like A versus BC, then more or less the state is written there in the Schmidt decomposition already. Yeah? Because it's somehow, I mean this is some weird that you can just look here these two things together. And then the Schmidt coefficients are 1 over square root of 2, which means that this thing, if I take a square, is 1/2. Yeah, so that means that for bipartite states, this overlap, if I take a biseparable state of the table, AB versus C or A versus BC, it's symmetric anyways, then this overlap is bounded by 1/2. But this means this thing, of course, is a larger family of states than the fully product states that I had before. So, and that means that this is a proper upper bound. And then you can see that, okay, in fact, there is in this state, this saturates it. So, yeah, so in principle, this is bisexual, but okay, it's also polycyclic, also saturates the state. And that means that for this state, this geometric measure is 1/2. Yeah, or 1 minus 1/2. Let's do it for the W state. And actually for the W state, you can do that, it will not work. It will not give the correct value. So what can you show for the W state? Actually, the W state is a symmetric state. Yeah, because it's symmetric on the parts ABC in exchange. So maybe the guess is that if you have such a symmetric state, then you can also take this symmetric, you just take AAA. You don't have to take ABC, that's the real product that you can take. It's the same. Actually, this can be rigorously proven. Yes. So that's. But then, if you do this, actually it's again easy for the W state because you have very few parameters. You have only one vector A to maximize. And if you look, it's only a single parameter which you have to optimize, and this you can just solve. So if you take this W state, yeah, you can essentially use this thing, you use this one parameter estimation, and then you get something like a value of 4/9. Which means 4/9 is smaller than 1/2. And this means that the overlap with product states for the W state is smaller than for the JZ state. And this means that the W state is more entangled than the JZ state in this measure. So you would say, so this is small, so the geometric measure would be 1 minus this, which is 5/9. And this is somewhat nice, or nice, it's somewhat surprising, because all the arguments that I showed you before always pointed a little bit that maybe the JZ state is more entangled than the W state. Yeah, but definitely this is just an example, it's a reasonable measure, you can prove it's a relative entanglement monotone, whatever, but there the W state is more entangled. Yes?
I'm sorry, I think I missed it, but how do you see that the W state is symmetric? Like translational symmetric or what kind of?
Symmetric means here, I mean, that I can make it, okay, I didn't explain this operates. This could be seen as a projector on the symmetric subspace, or you can also see that if I flip two arbitrary qubits of the W state, it always stays the same. Because, I mean, if you flip the first two qubits, I mean, on this term nothing happens, and this term is mapped to this term and vice versa. So just, I mean, you can also see that this is something like a bosonic state. Yes, in terms of these few fermions and bosons and quantization. There is something like a symmetric subspace, meaning you can exchange the particles without changing anything.
Okay. Is it the same in JZ or am I not seeing? Like in JZ you can also flip.
Exactly, yes. I mean, of course you're right. You can use the same calculation for the JZ, also with this trick. We would also get the same value of 1/2. But the point is here, I mean, the point is that for the JZ state, you can, I would say, even see it more easily. Yeah, you don't need this result, which is actually not so tricky. There was some question?
I have kind of the same question that the GHD said it's also symmetric, so I think it's the same question.
Okay, yes, the JZ of course is also symmetric, but I mean, that was just I want to show you a different trick. Okay, good. So, now you ask how can you compute such a quantity in general? I should say in general it's very hard. But for practical purposes there's a very nice trick which is actually useful to remember because similar arguments appear in entanglement theory at different instances. And it's the following. I want to compute for some state this maximal overlap. The idea is to make something like a seesaw iteration, where you have to optimize over A, B, C, over the three terms of the product vector, and you just fix two of them and optimize over the first one, and then you fix two others and optimize over the third one, and so on. And this simple idea is nice in this case because if you fix two of them, then making the optimization over one of them you can do analytically. So if you don't even have it's not a real optimization, you just write it down. Yeah? So So for instance, you take this psi, you fix B and C, and now you look at the state that remains if you apply the scalar probability between and C. Note that psi lives on A, B, C, so if you make the scalar product, something remains which lives on A. And then the optimal state is just the state that is proportional, or L is just the state that is proportional to this state. Of course, you have to normalize because it's not normalized. And then you just iterate. Yeah, so then you have the optimal A, now you fix, for instance, A and C and compute the optimal B, and so on, and you iterate, and this works very well. Yes. And some of up to 8 qubits is more or less gives you directly the best value. You have to iterate several times, but and I just want to show you such tricks actually occur frequently in entanglement theory where you have to optimize over some product structure and you do it about some iteration where you fix n minus one of them and the other one can be done analytically or with nested also. Yes?
Is it guaranteed that it reaches the global maximum?
No, it's not guaranteed. This is just a trick that works well in practice. There's no theoretical claim that this is a good trick, but it works. This is physicist. And of course, often we get some solutions which we can later prove to be optimal. Yeah, because once we have some of the guessing of the optimal state, then it helps. Good. Okay, let's finish with some properties of this geometric measure. Yeah, so at the moment I just told you, okay, so this is some measure, and well, it's there. This is the way. So, but what can you say about it? So first, actually, you can ask what is the interpretation in terms of physics? Because it's just you want to relate it to some physical interpretation. And therefore, the statement is the following: that you can show that if you have a set of states where all have a high geometric measure of entanglement, then it's very difficult to discriminate them with some local operational classical computation. Yeah, so in some sense you can, if you have spaces of states where all the states are highly entangled, you can somehow encode some information there, and it's something like hidden, or you can use it for something like secret sharing, in the sense that the parties locally, they cannot leave it out. Yeah, so they have to communicate, or they have to share some entanglement. Okay, maybe for, coming back from the mathematics. So actually this quantity has also a name in mathematics. It's called the injective tensor norm, and it's related to things like tensor eigenvalues and so on. So if you look into the literature, it's somewhat interesting that actually sometimes mathematicians and physicists talk about exactly the same thing in a completely different language. Yeah, I can give you some papers by mathematicians where we talk actually about this geometric, I would call it geometric measure of entanglement in terms of rings of polynomials and so on. Yeah, so. And there's one important issue which actually holds for many entanglement measures, and this is why I stress it here. What holds for this geometric measure of entanglement, that if you have a generic state of many particles, it's always highly entangled. Yeah, so these are somehow that if you just take a random state, random means in terms of random unitary, so you make something like a random unitary and draw your state according to that, then it will be highly entangled. And there are some rigorous results on this, but there also, I mean, you can just also plot it. Yeah, if you go for 3 particles, then this is the distribution of the geometric measure. Yeah, this, and you see, okay, that's somehow okay, entangled, and you see the maximal geometric entanglement is 0.55. This is 5/9, which is the W state. This is the maximum entangled state. Yeah, this is the distribution. And if you somehow go to more particles, then essentially all the states become very high. If you draw random states, very high entanglement. This is quite a generic property. There are some other works. If you take generic multi-qubit states and look for it at some bipartition, it will be very much entangled and so on. So this is it. Okay. Questions? Yes?
Shouldn't this be true if that's true for any entanglement measure, or for most of them?
Yes. I mean, this is what I want to stress. Yes, more or less for any entanglement measure, generic states are highly entangled. That's it. Yes?
On the first point, is it like you're highly entangled, their local stage would like go through maximum beats for.
Well, vaguely but not right. Actually, what you're saying now is that if a state is highly entangled, the marginals should be maximally mixed, which is good as something like indication, but actually it's not perfectly correct. Yeah, so they're definitely not a one-to-one consequence, they're counter states. I mean, where this result comes from is the following. If you make some local operation with classical communication, and you make some measurement to distinguish them, this will be some local measurement of the type A, tensor B, tensor C, tensor whatever, in the end. And now if you know that the states have a high geometric measure of entanglement, you know essentially that the overlap of all the types, like maybe of some effects of a measurement, like A tensor B tensor C, are somewhat small. And this means that there's no local measurement to distinguish them. That's roughly the idea. Okay, good. So, let's come into some mixed set. I just want to report some other factors. So, okay, this is again, I mean, Kombach is a well-known brewery in Germany. This lake is also. Good. Where did we stop? So we talked about Alice and Bob's shared quantum state. Yeah, and I told you that the more separable states are of this form, and otherwise they're entangled. And for mixed states, you take essentially convex combinations, which means you take a certain probability, you take essentially this. Great. This means there's a separability problem, which is just a question whether some state is entangled or not. And this is difficult. And what you should keep in mind, and this figure will occur later in my talk for the multi-bilat scenario, that's why I'm giving it here, that you can always should see it in this convex set, this egg-like picture, where you say the separable states are a convex set within the entangled states, or this within the set of all states. Yeah, this is something quite useful for understanding the consciousness. Then there was the PPT criterion, and just to remind you, the idea was, okay, there's some global transposition of a matrix, it doesn't change eigenvalues, but if you take something like a state operator X, which is an entangled product space, you can define something like a partial transposition, and this can change eigenvalues. And the main thing is that this is a good entanglement criterion in the following sense, that if a state is separable, then this partial transposition is positive, or it also says this state is PPT. That's a more or less a one-line proof. But yeah, this is a more one statement that partial transposition implies separability. It's one-to-one if you have for two qubits or qubit and a qubit, but in general it's not one-to-one. Yeah, and the structure is like that. Yeah, you have here all the states, here the separable states, and the PPT states are a little bit larger or could be a little bit larger, and yeah, these are the entangled states. And finally, what Anna also talked about is something about entanglement witnesses, just to recall the basic idea again, so that you have something like a witness, which means it's observable, which has something positive for separable states, and at least it's not entirely positive, but there's at least one state where it's negative, and that means that the state is to be entangled. And this you can then really use for entanglement detection. In a sense, you measure this one, and with that you can then decide whether it's entangled. And again, important is some of this picture. You have something like the separable states, entangled states, and here are some witnesses which somehow detect something. So this one is detecting this one, and this other one, this W2, is detecting a little bit less. It's only detecting this one. Yes. Yeah, you can always find a witness. They can be optimized. And you can see them as something like Bell inequalities, but contrary to Bell inequalities, you have to assume more or less that you do the correct measurements. I don't know, questions? Just to give you a simple example how this could work, and actually this works also in the multipartite case. Similarly, yeah, for instance, consider if you want to have a build state, and you want to prepare this, then for instance, a witness would be like this one, where you take essentially 1/2 minus this projection of the build state, and physically this means if the fidelity of the build state, which is more or less this operator, or this measurement of this operator, is larger than 1/2, the state is entangled. That means there's a threshold. Of course, if the fidelity is 1, then you have the perfect build state, it must be entangled. If the fidelity is very small, then you cannot say anything. Yeah, but in principle, the statement is that if the fidelity is larger than a certain threshold, then it's entangled. And yes, and this you can then, for instance, really measure. You can write this in terms of Pauli matrices, and you get essentially the 3 measurements of XX, Y, and ZZ. You can measure them. This was some old data from some photonics experiment. You get this result, and then you can calculate something. And you get this negative expectation value. And this means that yes, the state is entangled and actually just determine also the fidelity. This is just a very simple example how this could work. And in the multipartite scenario, I will write on some witnesses later. If more or less would work, the same thing, we just decompose it into some Paulis. Questions? So this was just some basic stuff which I need from Anna's lecture about bipartitions. Okay, let's come to the multipartite entanglement of states now. And okay, this is all you need. Good. So this slide more or less had before. Yeah, Tuesday. So in multipartite entanglement, first we have 3 parties, Alice, Bob, and Charlie. And there's these different classes, like this fully separable states, where we have 0, 0. We have this biseparable states, where something like Bob and Charlie are entangled, but Alice is separable. And there's these generally multipartite entangled states, which are like the JZ state or the Now we have to go to mixed states. And the idea of doing this for mixed states is the same as for the bipartite case. We just ask, can we see a state as some convex combination of probabilistic mixture of certain classes of state for the pure state? And recall that this convex combination just means that you can do it by LOCC. Yeah, because Alice, Bob, and Charlie, they can have a telephone and they can agree on some probabilities, where they say, look, we want to know prepare this state with this probability, and we do some coin or whatever, then we do some other state with another probability, and we do some coin and so on. But this is a completely classical protocol. Yeah, you just have to agree on some probability, so there's nothing quantum in it. And that means that this notion of this probabilistic mixture of states just corresponds to a certain generation procedure. So, how would it look? Let's start with some examples. So, for instance, what would be a fully separable state? A fully separable state would be some mixture of fully separable pure states. Meaning that you have certain probabilities, and with these probabilities you get these fully separable states. There's no entanglement whatsoever. Then there's things called biseparable states. And an example would be, for instance, this state. I mean, yes, it's not the most general state. For instance, you have something like entanglement between Alice, Bob, and Charlie is separated, plus with another probability, you have entanglement between Bob and Charlie, and Alice is separated. So it's important that in this notion, you essentially mix the different bipartitions. Yeah, that's why I gave this example. Yeah? So there's entanglement between Alice and Bob, Bob and Charlie, but you mix them and essentially still biseparable state. What would be something like a W-class state? A W-class state would be a state where you maybe need some W states to generate the state, but you do not need ZZ-class states. And because we have this different classes like ZZ-class and W-class, and we also mentioned that the W-class is somehow smaller than the ZZ-class because it's of value 0. So this is maybe the first thing that you want to do, that you sort of add some W states. And for instance, this would be an example. This is definitely because if you take a W state and mix it with a lower class, with something like a product state, and this is would be something like a state in the W class. Yeah, and of course, in the general scenario, if you take a general state, you also need some jet Z type states, and then you put in the jet Z class. And to give you an example, how this could look is the following state, which also correlated in my talk, which is something like the jet Z state mixed with white noise. So you can take, and maybe I can, from here. So these are all states. Here's the jet Z. And here's the identity. You can essentially look at these things, this set of states. Where you essentially start from this maximally white noise state, completely random, completely boring, and you end up in the jet Z state. And now this is of course separable. This is entangled. And now you ask, okay, there must be some threshold where it's here fully separable, and here it starts to be entangled. There must be another threshold where here it's still biseparable, and here it starts to be general multipartite entangled. And there must be another threshold where it starts to be here's a W class, and here's a jet Z class. Yeah. And this somehow characterizes this noise robustness of the state. And it looks, the values actually for this type of state are all exactly known. So it's known that if this P, the fraction of it is smaller than 1/4, or 1/5, which is very small, yeah, then it's, below that it's something like biseparable. And if you make it larger, yeah, then it becomes entangled, but until 3/7 it still stays biseparable. So, and then you have something like this, you cross this W class in some more or less a P smaller than 0.69, which is something, okay, there's actually an analytical expression, but it's quite long. And finally, you start to be in the jet Z class. And you can also see it like that. Okay, this would be something like the entire state space. Yeah, you see the identity is here, maybe the jet Z is here, and you move them always out, and at some point you leaving the fully separable sector, leaving the biseparable sector, and leaving the double class. This was essentially these three values. Okay, and in the end, you end up in this picture, which is something like, this generalization of the simple 2-egg-like picture for the bipartite case. Yeah, you have essentially the fully separable states, you have the biseparable states with respect to different bipartitions, but also you have the mixtures between these things, you have the W class and you have the jet Z class. Two facts which are not so trivial, or make me surprised. So one thing is first, the set of mixed W states is not of matter 0. While for pure states, the W states are of matter 0, this is not true for mixed states. Actually, this is in the end also not so surprising, because this is just the notion of this convex combination. Yeah? So for instance, if you if this is something like your extremal set, and you just have, for instance, 3 points, like this one, and this one, which are somewhere maybe like the W class. It's of measure 0, it's not much, yeah, because these are the pure states on the border. Now, if you just somehow take the convex combination of these 3 points, it's already this entire set, which is really something like a big fraction. Yeah, so that means that just because something is for pure states of measure 0, this doesn't mean if it's for mixed states, it can be anything. Okay, one other thing, which is, this is not so trivial, is following, that there are states which are separable for any bipartition, but they are not fully separable. Meaning that if you take some of these 3 leaves, and the intersection of this is not exactly the fully separable state. So it's not really, okay, should have plotted this more nicely. Yeah, but there are there are states which are separable for any bipartition, but not fully separable. Questions? Yes?
Sorry, is there any intervals between BAC and CAV?
What do you mean? Is there some? What do you mean?
Yes, the middle.
I didn't plot any lines here. Is this what you are worried about? Yes. You should think of this, that you really see this as, there's this there's something like B versus AC. This is maybe A versus BC. This is maybe C versus AB. This is fully separate. Maybe this would be the better thing. So, I mean, I didn't plot the lines there between these things. Yeah, and actually this will come in a later picture. You will draw the lines. Yes, that's just. Yes.
Is there any easy to see example for the second case? Because it seems to be partly good.
Not easy to see, I would say. But I can write it, give you explicitly if you ask me. Yes, I'll get that. But it's not, it would require 2 or 3 slides. It's not so easy. Okay. Again, once you have this picture, you can write down witnesses. Yeah? And you can write down witnesses, I mean, for the different classes of entanglement. You can have witnesses which just detect Z-type entanglement. You can have witnesses which just detect genuine multipartite entanglement, which are only positive and biseparable states. And you can detect kind of witnesses which just detect some entanglement, which might be just entanglement between 2 of them. And often these witnesses are similar as the example that I gave you, are essentially based on the fidelity. As if you, for instance, say, look, if something like my fidelity of the GZ state is larger than 1/2, then I know that the state is genuinely multipartite. Yeah, this is actually the logic, but not all of the witnesses. Okay, good. So now in the next 3-4 slides, I want to explain you how you can derive separability criteria for this genuine multipartite entanglement. And the point is, I mean, of course, in this picture, this genuine multipartite entanglement is the most interesting kind of entanglement. Why? Because this means that really all the 3 particles are entangled. Yeah, for instance, assume that we have some experimentalist who wants to make an experiment with 3 ions. And if he just proves some biseparable entanglement, it means that only 2 of the ions are entangled. Yeah, I mean, why should he then do some experiment with 3 ions if only entangled 2 of them? Yeah, so in principle, you want to use all the particles, so that's why this genuine multipartite entanglement is the most interesting. And the question is, can you write down some criteria? And we know that for 2 particles we have the PPT criterion, which is very simple. We can just evaluate it. Everything is nice. It's easy to understand. So the question is, can this be generalized to more particles? And if you do that, you see that there's a problem, namely that you have something like always this different bipartitions. Yeah, you have some of this entire green-yellow set here is a mixture of these different bipartitions. Yeah, and it's somewhat difficult to treat the set here of different bipartitions. So, what's the idea? The idea is to make some relaxation, in a sense looking at the larger set, which is, however, easier to characterize. And here, I use the set of PPT states, which I explained before is the larger set. So, geometrically, I'm doing the following thing. Yeah, I have something like the blue set, the blue lines, are the lines that I had before. Yeah, you have the 3 leaves of this ABC, BAC, and CAB, which is also what it's there. Now you see the now it makes the lines. Yeah, so that somehow it's just a different figure. Yeah, and instead of looking at this set, I just look at a little bit larger set because these were separable for A versus B, A versus BC, for instance. And I look at a slightly larger set where I just only request them to be PPT for this. Of course, I'm losing something, yeah, because it's a relaxation, but what, I can do it. And so instead of asking whether a state is something like biseparable for this, in this term, I just ask, is it a so-called PPT mixture? Can I write it somewhere like a convex combination of this red 3 leaves, which is something like this entire red set? And this is some of the trick that I can, instead of looking at this set, I look at this. So, why should I do that? I mean, first it looks completely crazy. Yeah, because I'm relaxing something, I'm just making the set larger. Yeah, and it looks a little bit stupid. But the point is, that this thing I can evaluate by a so-called semi-definite program. I don't know, who of you knows what a semi-definite program is? Who has written some semi-definite program? Okay, good. I mean, actually, I will have one slide about semi-definite programs coming after this. So if you do not know, wait for a second. Yeah? So, this, I mean, the point is this I can evaluate by something which is called semi-definite program, you will explain. And this is a very efficient numerical technique. And then it turns out that this is more or less actually, that this approximation is often quite good. So there are many states where this is just a precise approximation, where there is no gap between the red and the blue thing here, but this more or less precisely matches this. And you can also see then finding this violation as something like quantifiable. So, what is semi-definite program? I mean, roughly, I want to give a very short introduction, well, not really an introduction, maybe just a way of mentioning. Semi-definite program is the kind of optimization problems that you can solve. Okay, it's very simple. Yeah? But what does it mean? What does it mean? First, well, if you first, one thing is, if you have an optimization problem, like finding a minimum of a function, this is typically very difficult because you can never be sure that you have maybe some local minima. Yeah, and that's somehow that kills you because you cannot prove something. Semi-definite programs are a form of optimization problem where, under very weak conditions, you can prove that you found the global optimum. That means with semi-definite programs you can really prove something. It's not just a numerical technique. Yeah, you can really prove something. And that's why someone can sometimes really use it in proofs where you say at the end you boil it down to some semi-definite program. And yes, and it tells you it's bigger than 0, then it's bigger than 0. So, discussion. The structure is the following. You minimize some linear function, which is something like c times x, and x are variables, the c is a vector. A linear function. And the constraints are so-called semi-definite constraints, meaning that a certain combination of matrices, these are all matrices, has to be positive semi. And yes, and the main thing of this advantage is, I mean, what you should always remember is actually that you can find certified solutions where you really know that you have the global optimum based on something like reality. And the second important thing that you should always keep in mind that it's very simple. There are solvers for that where you can just need a few lines of code. You can use Mathematica, and one of the main solvers is Mosaic. But other solvers, so, but in principle, if you know a little bit of Mathematica, it's very easy, and you can do it with few lines. And you have to think a little bit, but okay, it's not really, it's not complicated. So, just want to give you some example. Taken some observable, and you want to find the maximal expectation value for PPT states. Is it a semi-definite program? Who thinks yes? Who thinks no? Now we have to decide. Who thinks yes? Who thinks no? Okay. Good. Why? Because look, this is quite this form. Yeah, because you have some linear functions that you maximize, and the constraints is that essentially what should rho be? Rho should be a state, it should be positive, and the partial transport should be positive. And these both conditions look roughly like that. Or you take some matrices which should be positive, some linear combination of rho and so on. Okay, you have to formalize it, you have to maybe express this rho as a block, the decomposition and so on. Yeah. Next thing. Given two states on A, B and BC, two marginals for three-partite state. And you may ask, is there some global state which has been this marginals? Is this an STP? Some, yeah. So who's in favor of an STP? Yeah, and it's getting less. Who thinks it's not an STP? Ah, okay, good. Okay, I'm sorry, it's still an STP. Why? This is the so-called feasibility problem. Now I'm just asking, actually I'm not maximizing anything here, there's nothing to maximize. But I'm asking, is there a matrix fulfilling certain positive constraints? Because I need looking for some matrix which is positive, and this matrix has to fulfill some actual linear constraints, namely that the margin of this guy should be this guy or this guy. So this more or less is something like an empty version of it. I just asked, is there some vector fulfilling this constraint? I don't want to minimize. And this is also more or less a minimizing of an empty function. Ask whether the maximum is 0 or near minus of something. So these are both STPs. Next problem. Let's assume the same thing. I take two marginals, and now I ask, is there some global pure state with these marginals? Is this an STP? Good. Yes. Why? Because this purity constraint is not a semi-definite constraint. Yeah? I mean, purity is means what trace rho squared is equal to 1, and trace rho squared is not something like a semi-definite constraint. So, no. Good. So, let's come back to this PPT mixture-like stuff. And now we can formulate it as an STP, and okay, I don't want to give you details, but essentially you can formulate it as something like optimization of the witnesses. We're looking for a witness which has a certain structure where certain matrices are positive. And in this form, it's clear in STP as I wrote it before. We minimize some function, linear function over some constraint that certain things are positive set. Yeah, so it's and yeah, then you can solve it. It's quite easy, and it works up to 7 qubits very well. Of course, at some point the dimension goes too big, and then it doesn't work anymore. Yes. And with that, you get some results. And for instance, these are now these similar things we look for different states. And you ask, okay, how much noise I can have. Actually, realize that this P is defined the other way around in the previous example. How much noise I can have to make it something like separator. And you see that essentially, for the GZ state, the exact value, this is 3 over 7 or 4 over 7 that I gave you before. But for other states, it improves drastically so that you can detect many more states with this approach. And also, you can, for instance, prove that for certain classes of states, for instance, for 3 qubits, which are permutational invariant. Yeah, you can take 3 qubit states and just like the W state makes them permutation invariant, and so on. And for these states, it's proven that this actually solves the problem. So this is an exact approximation, there's nothing more. And also you can then ask for generalizations, because now I used the T criterion and used it to lift it to making some criterion for general multiple entanglement. But you can also use other criteria like this computable cross-norm criterion or realignment criterion or some other positive maps. In principle, you can use more or less any other criteria that Anna explained and try to lift it. Okay. Questions? Yes?
Is the permutation, is the upper right box only for 3 qubits?
Yes, yes. This is in general for more than for 4 qubits. It will not work. It's just for 3 qubits.
Is there a generalization that works for more qubits?
Yes. So we have for instance summaries. If you say actually this maybe connects to what I will mention tomorrow in the lecture. If you consider states which are thrown diagonal in a GZ basis, and it's also necessary and sufficient. So there are other class of states where you can still prove that it's necessary and sufficient. But permutation is very not. Yes?
These new values, do they come because the PPT set is larger than the big bipartite separate? Or it's just kind of a new type of computation which allows us to get this multiplicity?
Yeah, wait. No. I mean, the idea of this prediction actually that these values are better. Yeah, so some of before you could, for instance, look at this state. This is some 4-qubit state. Doesn't matter what is precisely. With methods before, you could only prove that this is entangled up to this level with this 30% of noise. But now with this PPT mixer, you can prove that it's entangled up to 55% of noise. So it's better. It's a better value. Of course, I mean, I'm just saying, this is not necessarily the perfect value. The logic is some of this table is that, okay, with this PPT mixed approach gives you very good values or can characterize many entangled states where all the other criteria fail. It's still not true that this is optimal criterion. You're just saying, look, you improve a lot.
But this is not because the set is bigger. This is not because the PPT set is bigger.
No. It just says, okay, the PPT set is of course bigger, but due to the SDP, we can characterize this bigger set much better than the old set. That's the logic. Yeah, so. Good. Okay. Then maybe, okay, and I don't know how much time we have. 10 minutes, perfect. And I will talk now about another phenomenon, about superactivation. Now, Anna is looking very angry. And I will shift this network to Saturday. I'm sorry, I can. You can talk at the coffee break. Good. What is superactivation? But it fits better now than the network stuff. So, superactivation is a very simple phenomenon. It's surprising. I mean, consider two phones, and they're both broken. I mean, they're useless. I think you probably agree on that. Yeah, I mean, okay, this is a modern phone, this is an old-fashioned phone, but where you can cut something. Yeah, but if you have two phones that are broken, they're useless. Actually, if you look for quantum states or quantum resources, this is sometimes not the case. This phenomenon is called superactivation. And there are two things, simple things. So this was first observed in the notion of quantum channels. So, okay, if you have a quantum channel, you want to encode something, you have some noise, and you want to decode something. You hope to get some information out. And this is characterized by capacities of the channel. I don't want to go into details, but of course you can imagine. Some channels are good, some channels are bad. Yeah, and this tells us capacity. And what was observed, actually quite early already, is that for quantum channels you can have the case that two channels are useless, but if you combine them, they're useful. Yeah, so this channel has a zero capacity, this channel has a zero capacity. If you combine them, the capacity is not zero. So that's a little bit surprising. And this is essentially what is called superactivation. The two things can be more useful than single things. There's another example, and this comes from the notion of Bell neurology. I mean, okay, I didn't talk much detail about it, and also Anna didn't talk much in detail about it, but you know there's things like Bell's inequalities, yeah, which correspond to something like hidden variables. But there are also entangled states which do not violate any Bell. And these are states sometimes called local, because they do not violate any Bell inequalities. You have some state here, you distribute it, and you can have two things that Alice and Bob make measurements, but you can explain all the measurements in a classical way, so you don't violate any Bell. But then it has been shown that there are examples where if you take one state that is local, but if you take two states, they become non-local. Meaning that on these two copy states, you can make measurements which you cannot explain classically. Again, this is a little spooky. You can see, I mean, here you can explain it because if I have two copies, there are some more general measurements that I can do, which I cannot do on a single copy. Yeah, but some of this phenomenon of so-called 0 plus 0 is larger than 0. And this is more inside. So, now the question is, can we observe this also for multipartite entanglement? And the basic notion that is somehow, what is behind that is the so-called notion of tensor stability. And it's the following question. If I have something like a state, and it has a certain property, I can ask, does this property also hold for two copies of the state? Yeah, and these examples that I had before are more or less counterexamples that it can happen that it doesn't hold. For instance, what is tensor stable is a thing that if you have a separable state, and if you take two copies of it, it's also separable. And meaning separable now with respect to this larger bipartition. Yeah, so you have something like So you have here something like row A, B. And now you take a second copy, like a row, and maybe call this A prime, B prime, and now you ask for separability with respect to this guy. And this is, again, if two things are separable, this is the case. And PPT is a similar property. If a state is PPT, then also two copies of it are also PPT. The same split. But actually there was already quite early some interesting results taken as following. If you take separability criteria which are Kendall's table, they will not detect much or large dimensions. Which is more or less a mathematical result, but it tells you the following. That points for PPT, they entangle states which are very far away from the separable states. Yeah, meaning that in this egg-like picture, here's the separable ones, and here's the PPT ones, and here are some more ortho states. But the result states that this distance between PPT entangled states and separable states will become very, very large in the limit of large dimensions. Now you can ask, is also biseparability tensor state? Yeah, and so somehow this is the following statement that somehow, actually if you look at it, it's not so clear. Because if you take a state that is biseparable, maybe it's a biseparable decomposition of something A, B, C, A, B, C, and tau B, tau A, B, also B, C. So, if you take two copies of it, you get something like mixed terms between maybe this state and this thing, and it's not clear whether they're separable for this bipartition again. Yeah, so this is not completely trivial. And so this is now more or less a current problem, where several people are working on it. And essentially the statement is that general multipartite entanglement can also be subactivated. So you can have scenarios where you take one biseparable state, it is biseparable. If you take two copies of it, it becomes general multipartite. Yeah, so this is somehow, again, this picture of the ZZ state. Here takes the ZZ. Here's this white noise, and here's this threshold of this, here become entangled, here become GE. But in principle, there's a small, this light green region where you can essentially, okay, this is biseparable here, but if you take two copies of it, it becomes generally not entangled. And you can even go stronger. There's a result that essentially any state that is not separable for fixed bipartition, so any state more or less in this intersection here, will become GME if you only take very many copies. Yeah, so that's more quite a generic. Okay, questions? Yes?
Do you distill something from the two copies? Do you distill one state, which is or?
I mean, that's one of the ways how to prove that. So what was the first proof that this phenomenon exists? Going like that you take one state that is biseparable, meaning you take a state that is here. Yeah? You take two copies of it, and then you apply some tricky operation to reduce to single copies again and see, oh, this state is generally bipartite. Yeah, it's something like a kind of distillation. Yes. But one can also prove it's the other way around. I mean, there are other methods which are actually more strong. But one way of proving it is like just if you say you take two copies, you reduce it to one copy again, and then apply one of the known criteria for entanglement. Yes?
In the case of superactivation using two copies of density matrices, is there any condition to the density matrices? Because it feels like they have to be entangled but local, or is it also for fully separable density matrices you can do this?
You mean wait.
The single density matrices themselves, do they have to?
Yes, I mean they should not be separable for fixed bipartition. Yeah, if as soon as they're separable for fixed bipartition, more or less this applies. Yeah, if you for fixed bipartition you can take as many copies as you want, you will never get rid of the separability. Yeah, but as long as for all other cases, at some point they will come. Okay, good. Then I maybe. Sorry, Anna. I come to my conclusion. So, I mean, what did I tell you? Essentially only the first 3 points. So there are somehow like different and inequivalent measures for multiplying entanglement. There's something like a generalization of the PPT criterion, which you can use for character entanglement. And finally, I talked to you a little bit about this notion of superactivation, which I personally find quite interesting because it tells you maybe something about using this multiplier entanglement as a resource. It gives you some new insights. Okay, that's all for the moment. Thanks.
Thank you, Otfried. We had plenty of questions already, but maybe you still more. We have one back there.
Thank you. I'm just referring to a work by Gühne, who actually showed entanglement between 2 microscopic oscillators with a very tailored entanglement witness. And so my question as an experimentalist is, if you have a very exotic system in the lab, how do you know or how do you find the best entanglement witness for your system, or for your setup? Because to me, this one in this paper, it's just brought up, but it's very tailored to the problem. And if I start, how do I know which one is the most suitable?
I mean, there are 2 different questions. So first, if you, or 2 different relevant things to consider. So first, typically an experimentalist has some idea which states they want to prepare. Yeah, so you may be aiming at a GZ state, a W state, so on. And this gives you some constraint on the witness in the sense that you maybe look for fidelity witness for the GZ state, fidelity for W state in a certain basis, because it also depends on the basis. Yeah, so you can design your witness specifically for a given target state. And also, what I said here in the terms of this thing. Yeah, so in principle, this is also like in the end, what you give you, it gives you a witness. If you have some target state, yeah, the semi-definite program will give you the witness, which is good. Yeah? So in principle, this of course the conclusion that you later draw as a state of entangled does not depend on the choice of the witness. The second thing, which is also relevant for experimentals, is often that they cannot measure everything. Yeah, I mean, in this abstract theory, typically, at first instance, you can measure everything or measure all the Pauli's or whatever. But typically, if you talk to experimentalists, they tell you, oh, yeah, we can maybe something more easy or something we cannot measure at all or very difficult with bad statistics, whatever. And then you always have to tailor the witness somehow to these constraints that you have. This is, I mean, sometimes one can do it systematically. For instance, in this approach, you can also partly put constraints on the measurements that you can do by putting extra constraints on those operators, that they should be measurable with certain observables that you have. Yeah, but on the other hand, often also it's like that you have something like a witness, and the experimenters tell you, oh, we cannot measure this, and then you try to modify this witness and maybe make it a little bit weaker. Yes, in this shifting, you make it weaker, but on the other hand, make it easier to measure for them, and then you hopefully find a solution. But it always strongly depends on that.
Okay, thanks.
Hi, thank you for your lecture. I was wondering if you could talk a bit more about the relationship between superactivation and entanglement distillation, because it seems very counterintuitive to me that you can have some entangled states that are not distillable, like you cannot get more entanglement from them, but then you can have, for example, biseparable states that are not even entangled, and then when you take several copies, you get entanglement.
Wait. Okay. I mean, actually, if you say there are some states which are not distillable, you have to be careful with the statement because often it's meaning that the state is not distillable is just a short version of no one has found a distillation protocol yet. Yeah. So I mean, there's this big question about this NPT bound entangled states, which means that there should be some states which violate the NPT criterion, but still they cannot be distilled. And there's essentially, this is exactly the problem, yeah, so one just doesn't know protocol, yeah, so, okay. On the other hand, I should also say that this, I mean, I would still say that superactivation and visibility are quite different, because, I mean, superactivation, I just take 2 copies and look are they GME or entangled in some assistance useful for something. In distillation protocols, I can actively do something with my state. I can make measurements, and depending on the measurement, I make something on the second copy and so on. So I would say it's a little bit different thing. Also, it's a different thing because the superactivation is mainly not for multipartite entanglement and not for bipartite. Yeah, so it's
Okay, thank you.
so closely connected.
One last question here. Hi, thank you for the talk. I was wondering if it's possible to characterize the multipartite entanglement looking only at, for example, reduce density matrices between 2 subsystems. So, like, if I have 3 and I show that row AB is entangled, and the same for BC and CA, does that mean that, like, the whole state is non-separable?
Depends. So first, I mean, first the question, what you said. I mean, there are instances of states where, for instance, where all the bipartite states, the views are separable, but still the global state is entangled. So it's not so, there's not so just a one-to-one correspondence. I mean, first we know that there are highly entangled states, like you had said, where the margins are separable. On the other hand, yes, so they're different, you cannot take one-to-one correspondence. What is interesting, or what is, I mean, what also people work on, is the following question. So let's assume I have my state, I know the marginals, and now I don't care whether the marginals are entangled or separable, but I just can I prove the entanglement just from these marginals? Yeah, so that's, I mean, and actually this is quite relevant because in many experiments you can only measure the marginals. Yeah, in some spin splitting experiments you truly measure these marginals, but you cannot measure 3-body correlation. And there's a lot of theory about this question. How can you prove multipartite entanglement from the marginals? And actually this is a little bit coming to this question before, it's related, because you can say, if I just know my marginals, this means just I can only measure a certain set of observables. And mathematically it's often equivalent, in the sense that you just ask, okay, well, can I write down similar witnesses under the constraint that I only have 2-body correlations and not 3-body correlations.
But like in the case where I show that all the marginals are entangled, can I conclude that the whole state is multipartite entangled?
Okay, well, in general I would say no. Of course, the W state would be a counterexample to my statement, because if you know that all the marginals are really as entangled as the W state, then there's only one state that is compatible with the global W state. But in general, I think just if you have some entanglement in the marginals, this does not mean that the global state is.
All right, let's thank Otfried again.